Welcome back to my channel. This is my second lecture of this gravity and gravitation series. I discussed some of the historical background regarding the gravitation and also discussed Kepler's law of planetary motion. If you haven't watched it, please do watch it for continuity. Today I will cover Newton's law of gravitation, and at the end of this video I will discuss something about this law of gravitation which nowadays most of the textbooks keeps. Let's get started. What does the law of gravitation tells? The law of gravitation tells that everybody in this universe attracts each other along the line of joining their center of mass, and this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, let us just refer to this figure where we have drawn the three coordinate axes x, y and the z, and we have shown two bodies. Suppose we name this one by A and this one by B. Okay, and let with respect to the origin O, R1 is the position vector of the object A, R2 be the position vector of the object B, and let R be the position of B with respect to A. Okay, then the force of gravitation on A due to the object B, let it be Fa. Okay, then according to Newton, this force Fa will be proportional to the product of the mass of the object A and object B. So it will be like F is proportional to ma times mb, and then again this force Fa due to the object B will be proportional to the distance of separation between these two objects. So Fa is also proportional to 1 upon r square. Okay, where r is nothing but this quantity and r equals this, right? Now then, combining these two relations, we can write that Fa is proportional to ma times mb upon r square and r cap. Okay, this can be written as Fa equals some constant g ma times mb by r square and then r cap. Okay, so this gives a force acting on the object A due to the object B. Okay, and this is basically the mathematical form of Newton's law of gravitation. Okay, here G is nothing but the constant of proportionality and is termed as the universal gravitational constant. Okay, now if you wish to calculate the force on the object B due to the object A, okay, then simply we write this as Fb equals to G ma mb by r square r cap with a minus sign here. So you can see that Fa and Fb are equal in magnitude, but directionally they are opposite. So simply Fa is equals to minus of Fb. Okay, so this is basically the Newton's law of gravitation in mathematical form. So in general we can write this as F is equal to G m1 m2 upon r square, where m1 and m2 are the masses of any two objects of the universe, and r is the distance of separation between their centers. Then this gives the force acting upon the two bodies, and remember that the force acts in a similar manner in both of the object but in a opposite direction. Okay, now let us discuss about the universal gravitation. So what is the universal gravitation? We get this universal gravitation as a consequence of Newton's law of gravitation, and the value of universal gravitation is 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Okay, this is the value of the universal gravitational constant. The value of the universal gravitational constant capital G was calculated by Cavendish, and this value remains same for everything, and it is not affected, not disturbed by any factors. That's why it is called the universal gravitational constant. Now you may say, how to find out this unit This is very easy. How we can calculate the unit of universal gravitation constant? Let's do this. So we have the Newton's law of gravitation as F equals to G, then there is two masses, product m1 m2 upon r square, and this gives that G equals to F r square upon m1 m2, right? Then we readily find that the unit of G depends on the unit of force, unit of some distance square, and the unit of these two masses. Okay, then we write that unit of G is equals to nothing but the unit of force times unit of r square upon unit of m1 and unit of m2. We simply put the unit of these quantities. Okay, we simply put the unit of all these quantities. Then in SI system, what we get? In SI system, if we put this unit, we get the unit of G in SI system. So force is Newton, r is nothing but some distance, so it's meter square, upon unit of m1 is kg, similarly unit of m2 is kg. So this simplifies Newton meter square kg to the power minus 2. In similar manner, we can write the unit of G, capital G, in CGS unit system as G equals dyne semi square gram to the power minus 2. So this is how we get the unit of universal gravitational constant. Now if you wish to calculate the dimension of G, this can also be done from this relation. Okay, so the dimension of G, we write dimension within the third bracket. So dimension of G is nothing but the dimension of the force times the dimension of the distance square between the two objects and the dimension of the mass m1 and the mass m2. Okay, so just put this dimension. The dimension of m is m, capital M, L, t to the power minus 2. Dimension of r is nothing but length square, so this L square, and the dimension of m1 is m and dimension of m2 is also m, so it's m square in the denominator. Okay, and all these things simplifies to m to the power minus 1 L cube t to the power minus 2. So this is the dimension of G. Now all this being said and all this being done about the universal law of gravitation, that F is equal to G m1 m2 upon r square, and that Newton, we have accepted the fact that the gravitational force is proportional to the product of the masses of the two objects in concern and is inversely proportional to the square of the distance between the two objects. But how to justify these two fundamental bases of Newton's law of gravitation? How we just accept this fact that this should be true? So let's try to understand the basis upon which Newton give this universal law of gravitation, right? So each of us know the story of an apple falling on Sir Newton while he was sitting in the garden, and from there he gets the idea of gravity and gravitation. So I don't know how much truth is in there because I don't know actually, but the fact is what Sir Isaac Newton already knew, that the distance of the moon from the earth, which was 3.84 into 10 to the power 8 meter, and Sir Newton also knew the radius of the earth, and he also knew Galileo's law of falling objects, right? So with these ideas, Newton gave his universal law of gravitational motion. So what was Galileo's law of fall? It was nothing but Galileo said that every free falling object will be subjected to acceleration irrespective of their masses. So you can see that here I have shown two objects, one of them is a heavier one and one of them is a lighter one, but when they are free falling they kind of fall with the same acceleration. Okay, so let us just justify one by one how Galileo's idea was used in order to get to the Newton's law of gravitation, right. So let us first try to justify the first assumption, in which Newton say that F is proportional to the square of the distance between the two objects. Let R represent the square, R represent the distance between the two objects. Suppose the moon is revolving in an orbit of radius r. Moon is revolving around the earth in an orbit of radius rm. This is the radius of the orbit of the moon. Radius of the orbit of the moon. Radius of the orbit of the moon. Right. Then, since it is rotating about the earth, it is subjected to a centripetal acceleration due to the gravity of the earth, right. Let am represents the centripetal acceleration of the moon due to its rotation around the earth due to earth's gravity. So am will be v square by rm, and this is equals to 4 pi squared rm upon t square. Okay, so what is v here? V is nothing but the velocity of the moon, and t is the time period required for the moon to complete a rotation around the earth. So v and t is related with each other with this relation twice pi rm upon t. Okay, now I have already stated that during Newton's time he already knew this t and this rm. Okay, so if we put this value, then we get am equals to 0.002736 meter per second square. Okay, t equals 27.3 days. This is the centripetal acceleration acted upon by the orbiting moon due to the gravity of the earth, and observe that this clearly shows that the force due to earth's gravity decreases with distance. So the force of gravity on the moon is much lesser because it is away from its surface. So this is the logic behind the statement that the force due to earth's gravity decreases with the distance, but we haven't yet justified the fact that how it decreases, what is the relation. So let us just assume that the gravitational force due to the earth is inversely proportional to the square of the distance. Let us just assume this is just an assumption, okay, that F is inversely proportional to the distance square. Okay, we have to prove this. Initially we are assuming this, but finally we have to prove this. If we can't prove, this assumption will be invalid. Okay, so if we assume that the gravitational force due to earth is inversely proportional to the square of the distance from the center of earth, then we can write that am is proportional to rm to the power minus 2 and t is proportional to re to the power minus 2. Re is nothing but the radius of the earth. Okay, Re is nothing but the radius of the earth, and it has a value 6400 kilometers. So from these two relation we can write that G by am equals rm square upon re square. Okay, and if we put this, the value of rm and re, this turns out to be this approx. Okay, therefore G equals to 3600 times this quantity. Okay, put this value 0.0027336, and this actually turns out 9.8 meter per second square, and wow, this is actually the value of g at the surface, right? So our assumption that f is proportional to the inversely proportional to the square of the distance is correct, right? So this is how Newtons came to the idea that the force of gravitation have to be inversely proportional to the square of the distance. Okay, right. Now let us try to justify how Newton arrived at another conclusion, that the force F must be proportional to the product of the two masses, not proportional to, say, the sum of the two objects, mass objects, right? Why Newton accepted this one and not this one? Okay, let us try to understand why. As I already told that Newton already knew that there at the surface of the earth different mass fall at the same rate, that is with the same acceleration. Also Newton with his second law of motion, and that is force equals mass time acceleration, right? Mass time acceleration. Okay, this relation Newton already gave, force equals to mass time acceleration. So by Newton's second law of motion, all falling bodies near the surface of earth, the gravitational force must be proportional to the mass of the object. Why? Because as per Galileo, every falling object have this acceleration constant, right? Every falling object has this part as constant. So the gravitational force should be proportional to the mass of the falling object, correct? Right. So why does this really matter, that the proportionality of the mass with the gravitational force? Why does it really matter? It really matters because if gravitational force depends on the sum of the masses of earth and the object m, let us assume here that the gravitational force F is some function or depends upon the sum of the mass of the earth and the falling object. Let us assume that if F depends upon the gravitational force, F depends upon the mass of the earth and depends upon the sum of the mass of the earth and the object, then this essentially means that the same exact force should act for a body of mass 10 kg and for a body of mass 1 kg, right? And why it is that? Because this 10 kg and this 1 kg are so small with respect to the mass of the earth, so it is insignificant to compare with the mass of the earth. So this in turn implies the lighter one would accelerate 10 times as fast as the heavier one, but it is not what we observe. What we observe is already said by Galileo, that every falling body will be accelerated with a constant acceleration. That means they will fall at a same speed with the same acceleration. Okay, so if the gravitational force cannot depend as this. Gravitational force cannot depend as this, as the sum of the masses of the two objects. Okay, the logical assumption should be that the gravitational force should depend on the product of the two objects, and if we assume this manner, that F be proportional to the mass of the earth and the mass of the object, then what happens? When you calculate the acceleration of that object, okay, when we calculate the acceleration of that object, it becomes independent of its own mass. It becomes independent of its own mass. It becomes independent of its own mass. So every falling object under the gravity of earth falls with the same acceleration, which is independent of its own mass, right? So Newton accepted this idea that the gravitational force should be proportional to the product of the two masses, gravitational force F should be proportional to the product of the masses in concern, not proportional to their sum. Okay. So I think I was able to explain how Newton came to the idea that the force of gravitation is inversely proportional to the square of the distance between the objects, and how the force of gravitation depends on the product of the two objects in concern. Okay. So I hope you were able to understand today's class. What I have just spoken you, it was Newton's law of gravitation and the unit and dimension of the gravitational constant with the mathematical form of Newton's law of gravitation. Okay. If you have any queries regarding this Newton's law of gravitation, you can always ask me in the comment section, and if you like this video, I wish a like and your comments and a subscription from you. Thank you very much. In our next class, we will discuss the different factors upon which the acceleration due to gravity, that is small g, varies.